Okay, so welcome to this next video in the playlist on experimental techniques. In this video, what we're going to talk about is measuring calcium concentration using Fluo-4. Okay, so this video is going to be on Fluo-4. So, the structure for this video then, we're going to start off with the basic principle of how you can use Fluo-4 to measure the level of calcium. Okay, and what's special about Fluo-4 is that you can actually use it to measure the calcium concentration within cells. We'll come to how we can use it to measure the calcium concentration within cells right at the end. We will for now keep it nice and simple and think about just trying to measure the concentration of calcium within some beaker, okay, within some solution in some beaker. Okay, so we've got some beaker here. And the basic problem is that this beaker is full of a solution and we want to know what is the concentration of calcium. So square brackets around calcium means concentration of calcium. So we want to know what this is. Okay, and basically Fluo-4 is going to allow us to do that. Okay, so we're going to start off with a discussion of fluorescence, okay, because Fluo-4 is a fluorophore, hence the name Fluo, okay, and the fluorescence properties of Fluo-4 are going to be increased when it binds to calcium, and that is how we're going to measure the calcium concentration, by looking at the increase in the fluorescence of Fluo-4. Okay, so let's just have a brief reminder of what the concept of fluorescence is. So basically, the concept of fluorescence is that certain molecules, okay, and I'll just draw a molecule as a blob, but you can imagine that this maybe is Fluo-4. So Fluo-4 is some chemical, okay, you can Google the structure of it if you wish, okay, it's some chemical, and basically it can absorb light of a certain wavelength, okay, so we'll call this the frequency, which of course is related to the wavelength, the frequency of excitation, okay, and then it will get the energy that it gets from this photon, from absorbing this photon of the excitation frequency. It will gain some energy, and it can then re-release that energy in the form of another photon, but this photon will have a lower frequency than this photon over here. Okay, so this photon will be the frequency of emission. Okay, and basically, whilst the frequency goes down, so the frequency of emission will always be lower than the frequency of excitation, the wavelength goes up, because the wavelength is inversely proportional to the frequency. So the exact equation relating them is that the wavelength is equal to the speed of light divided by the frequency, basically. Okay, right, so if the frequency goes down between excitation and emission, then the wavelength is going to go up, basically. So, for Fluo-4, the excitation wavelength, okay, so the wavelength of excitation is around 490 nanometers, okay, whilst the wavelength of emission, which needs to be slightly longer, is 520 nanometers. So it absorbs in a sort of bluey region, okay, of 490 nanometers, and it emits in a sort of greeny region of 520 nanometers. That is the phenomenon of fluorescence, where you can shine light of one color, or in fact it doesn't necessarily need to be visible light. It can be other frequencies of electromagnetic radiation which are not visible. Okay, you shine electromagnetic radiation of one frequency on and get another frequency coming off, and that other frequency is always lower, okay, so carries less energy. So the example here, we're shining blue light on and we're getting green light coming back at us. Okay, so basically Fluo-4 is a fluorescent molecule. It will produce fluorescence. Okay, so if I just produce a solution that contains absolutely no calcium, so imagine this is a solution which contains no calcium, and I put in loads of Fluo-4 into this solution, then basically if I shine blue light on, okay, let's say I shine light of wavelength 490 nanometers onto this Fluo-4 containing solution, then what I will get coming off is some green light. I can now detect this green light basically. I can detect the intensity of the green light coming off, and I can get some readout for the intensity of the green light that is being produced by this Fluo-4 containing solution. Now, basically this is the amazing thing. Fluo-4 can bind to calcium. Okay, so if we represent our Fluo-4 molecule as this rectangle here, okay, it can bind to a calcium ion. So here is our calcium ion. So it can bind to a calcium ion, and basically when you have this Fluo-4 calcium ion complex here, this is far better at performing fluorescence. Okay, so this is much better at performing fluorescence than Fluo-4 is on its own. So the chance that it will absorb the blue photon is much greater, and of course once it's absorbed the blue photon, it will then emit a green photon. So basically, if you now put calcium into this solution containing Fluo-4, your fluorescence, the amount of green light you are getting produced, will go up, because now the calcium ions are binding to the Fluo-4 molecules, and those Fluo-4 molecules are having their fluorescent properties enhanced basically. Okay, so this is the idea, okay? We could use this to measure the level of calcium in here, okay? Because if we add Fluo-4, then the fluorescence will increase for Fluo-4 above what it would be if there was no calcium present, by an amount that is proportional to how much calcium is present, i.e. proportional to the calcium concentration. So let's now actually discuss how we do this then. So basically this is what you would do. You would take your solution which contains the calcium, and we want to find out what concentration of calcium you have within this solution. So here is our test solution basically. So we want to know what is the calcium concentration within this test solution. Okay, so here's our test solution, so I'll just label it up as the test solution. Okay, and it contains loads of calcium ions, and I think I will colour calcium ions in orange here. So it's got loads of calcium ions in, and we want to know what's the concentration of calcium ions in there. Okay, right. So basically what we're going to do is now we're going to add a certain amount of Fluo-4. Okay, right, so in we put Fluo-4. Now in principle what we could do is we could know exactly how much Fluo-4 we've added, and we could then go to some table which would tell us for that amount of Fluo-4 and for the amount of fluorescence that you then get off, how much the calcium concentration must have been. However, we're going to do it a cleverer way basically, and for the way we're going to do it, it doesn't actually matter that you know how much Fluo-4 you add. So this is why it's a better way of doing it, because even if you try to make sure that you put in a certain amount of Fluo-4, you have to make sure that the concentration's correct. So there's an error in your amount of Fluo-4 that you put in. There's also the error of the volume that it'll be, and therefore the concentration it'll be. So there's a better way of doing it basically than trying to get an exact concentration of Fluo-4 within this solution. Okay, so basically just add in Fluo-4 willy-nilly. I don't care how much you add in. Okay, so put in your Fluo-4. You need to put in enough that it won't be saturated, i.e. you need to put in enough so that this calcium concentration that you've got here isn't going to be enough to completely saturate every Fluo-4 molecule, i.e. you won't get a calcium molecule bound to every Fluo-4. Okay, right, but that's the only thing that you need to get right. Okay, so you add in your Fluo-4, and now what you will do is you'll perform this measurement. So you'll shine blue light on, okay, and of course you'll get green light coming back off now. Now, some of the Fluo-4 molecules will have calcium bound to them, okay? So within our solution, what we'll have is a mixture. Some Fluo-4 molecules will not have calcium bound to them, but some of them will have calcium bound to them. Now, of course, the ones which do have calcium bound to them, those are going to be better at fluorescing than the ones which don't. So, the amount of green light that you get back, the amount of fluorescence that you're going to get being produced by this solution will be greater than if you had no calcium present. But it won't be the absolutely maximum amount of fluorescence that you could get, which is if every single Fluo-4 molecule had a calcium bound to it. Okay, right, so we will then measure the amount of green light coming off. Okay, the intensity of the green light, and we'll call this F for fluorescence. Right, okay, so what we now need to know is two more things. We need to know the absolute minimum fluorescence that you could get, okay, which is if all the Fluo-4 molecules didn't have calcium, okay, so what we now need to do is make sure that none of the Fluo-4 molecules are bound to calcium. Now, how are we going to do that? Well, basically, what we're going to now add into our solution is a molecule called bapta. Okay, now bapta is what's known as a calcium chelator. This is a molecule which will bind to calcium. Okay, so the idea is that if we put in this bapta molecule into our solution, it will sequester all of the calcium molecules. So what we're going to do is, this is our solution here, our test solution. We're going to add a little bit of bapta in, and basically what's going to happen is the bapta molecule, so if this is a bapta molecule here in red, it's going to sequester the calcium ions. So calcium ions will bind to it, and the idea is that we're going to end up with no free calcium in the solution. All of the calcium ions will be bound to the bapta molecules, okay? Like so. So, basically, this will mean that there will be no calcium free to bind with the Fluo-4. All of the calcium will end up bound to the bapta rather than the Fluo-4. So now, what will be the case is that all the Fluo-4 molecules, and I think I'll denote Fluo-4 in a certain colour. I'll denote Fluo-4 in turquoise. Okay? So the idea is that all of these Fluo-4 molecules now, which I'll just show as these little lines here, they won't be bound to calcium anymore. Okay, so all of the Fluo-4 molecules will be free, so that all of them will have their less good fluorescent properties because they haven't got calcium bound to them. So now when you shine the same intensity blue light on, and of course that we can fix, okay, so you'll shine the same intensity blue light on, now you will get less green light coming back. Okay, and that's the minimum fluorescence that you could possibly get. So this is F min, basically. Okay, so you'll record the intensity of the light that comes back when you have added bapta, and therefore where there is no free calcium, and where all of the Fluo-4 molecules in your solution are free and don't have calcium bound to them. Okay, and this tiny little intensity, this will be called our F min, and I'll show you how we're going to use all of this to calculate the free calcium concentration in a moment. Okay, now before we go any further, I would just like to discuss with you the structure of bapta. Okay, so bapta is short for 1,2-bis O-aminophenoxyethane NNNN, and then tetraacetic acid. Okay, so this is short for 1,2, and then we have bis, and then it's O-aminophenoxy. Okay, so O-aminophenoxy, and then ethane, out of brackets, and then finally N, 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 and then a final N, and then tetraacetic acid. So let me show you the logic in calling it this. Okay, so here we have tetraacetic acid. Right, so let me show you the structure of this firstly. So basically the whole thing is based on ethane, okay, which is just a 2-carbon hydrocarbon. So let's put our ethane right at the center here. Okay, so here's our ethane. Now coming off the ethane, off the first and the second carbon of the ethane, you have 2 O-aminophenoxy groups. Okay, so basically you have 2 oxygens coming off, and I just want to firstly just start off by circling the ethane here and highlighting that in red over there. Okay, then you have these 2 oxygens coming off, that's the oxy here, and then coming off the oxygens you then have a benzene ring, that's the phenoxy. So off the oxy group you then have a benzene ring. So here's a benzene ring, here is another benzene ring on this side, so everything's beautifully symmetric always in this molecule. Okay, like so. Right, so these groups now, these are the phenoxy. Now we haven't got to the aminophenoxy yet, okay, so I will just deal with the phenoxy at the moment. So here is the phenoxy. Now both of these benzene rings are going to have amino groups coming off. Now the way this is usually drawn is you have the amino group off here coming down like so, and the amino group up here going up like so. That's just to make the picture look prettier. You could of course have it coming down here as well, there's no difference between that. Okay, right, and then coming off these nitrogens you then have 4 acetic acid groups. Okay, so let's just continue on with our highlighting. So this nitrogen is the amino, okay, and then this final bit down here, this N-N-N-N-N-N tetraacetic acid, basically off these nitrogens you're going to have acetic acid groups, okay, so 2-carbon carboxylic acid groups like so. Okay, so here are 2-carbon carboxylic acid groups, and off each of the nitrogens you're going to have 2 of these, like so. So here's CH2, and then we've got another acetic acid group here, and then we've got another acetic acid group over here, like so. Okay, right, so here is the tetraacetic acid. We've got 4 acetic acid groups and they come off the nitrogens basically. That's what that is telling you. Okay, so acetic acid is just the old name for 2-carbon carboxylic acid. It's the old name for ethanoic acid, or what's in vinegar. Right, okay, so this is the structure of BAPTA, and basically it's a calcium chelator. Okay, right, so we use BAPTA, we add it, and that chelates all the calcium. There's no free calcium anymore. That means all the Fluo-4 molecules are on their own. That means the fluorescence that we get should be at its absolute minimum, and we're going to need that in order to be able to work out what this number here, this F that we got here from our original test solution with the normal, with the original free calcium concentration, what that actually means, i.e. how to get from that to calcium concentration. Okay, right. Let's now talk about the other final piece of information we need. We also need what's called the Fmax, which is the absolute maximum fluorescence you could get. Now, how would you get the absolute maximum fluorescence that you could get for the number of Fluo-4 molecules that you have within this solution? Okay. Well, you bind calcium to absolutely every single one of them. So now what you'll do is you'll take the same test solution and basically you will add loads of calcium chloride. Now yes, you've added a bit of BAPTA in here, but you will add so much calcium chloride that it will completely saturate all the BAPTA that we've just been dealing with. And then it will not only saturate the BAPTA, but it will then move on to saturating the Fluo-4 molecules. So basically, here we have our BAPTA molecules, so I'll put those in. So they're still here, and they're going to get saturated by calcium. So let me show this. So they're all saturated. Whoops, they're saturated by calcium. Then we're going to put so much calcium in that all the Fluo-4 molecules, and I'll show the Fluo-4 molecules in turquoise here, all the Fluo-4 molecules also get calcium bound to them. Okay, so here's calcium, here's calcium, here's calcium, here's calcium, here's calcium, and here's calcium. Okay, right. Basically now all of the Fluo-4 molecules have calcium bound to them, so when we shine in our same intensity blue light, the amount of green light we get out will be the absolute maximum. I'm sorry, I didn't mean to suggest that the amount of green light we're getting out is more than the amount of blue light we're putting in. That's silly, but basically you get the message that this is the absolute maximum amount of green light you could have ever hoped to get out, basically. Okay, you record the intensity of that, that's F max. Okay, right, so we've now got all of the pieces of information we need. F, which was, remember, the intensity of the green light that we were getting out when we just added the Fluo-4 to our original calcium test solution, okay, so we hadn't added Bapta or anything else like that. F min, which was when we added the Bapta to our test solution to bind to all of the free calcium molecules and result in no free calcium left in the solution, which means that there will be no calcium bound to the Fluo-4, which means that Fluo-4's fluorescent ability is at its lowest, and then the amount of green light that we get coming out at us is going to be at its minimum. And then F max, which is basically where we completely saturate both the Bapta and the Fluo-4 with calcium, so that Fluo-4 is now all bound to calcium. All of the Fluo-4 molecules in our solution are bound to calcium, and the fluorescence we get is at its absolute maximum. Okay, I claim that from these 3 pieces of information we can work out, well, actually we'll need one more thing, okay, which I'll explain in the next video, but that's something that we can just get out of a textbook, okay. That will allow us to get to the calcium concentration that was in our initial solution. Okay, right, and I'll show you how in the next video.